All right, this is the video for module 27, which is net force. So let's go to the notes for net force. I'm going to click on tug of war. You should too. It's a fun little simulation we're going to explore. I'm going to open that, and just to get set up, let's copy your notes 2 on net force. So you're getting a Google Doc, notes 2 net force, make a copy. Of course, once it's loading, move it into the correct folder. There you go. So in this lesson, we're going to learn what happens when there is more than one force acting on an object. Most of the time, there's more than one force affecting an object. And we're going to answer the question, how do forces affect the motion of an object? So we're going to look at a bunch of arrows with numbers. We're going to find a net force, and we're going to tell how that force is going to change the object's motion. All right, so we're just going to use the slides that are embedded in this page again. First, let's go back to that tug of war. So we've got a blue team and a red team. We have the same 4 players. We have small guys. We've got medium guys. I like to check the sum and the values of the forces so I can predict exactly what's going to happen with accuracy. So if I tell these 2 people to go, as you might expect, the red team is going to start winning. Now, what if I pause that and I have some teammates join the blue team, okay, to try and even it out? So now the forces equal 0. Well, why didn't it stop? Why did the red team still win? Well, the answer is because that rope, that cart, was already in motion. So having balanced forces would not make it actually stop. It would just make it continue going the same direction it was going. Let's try another scenario. Now we're going to make the blue team a little bit stronger. Okay, blue team starting. Now, what if I overpower the blue team with the red team? Okay, give them all the guys. Now they have 350 versus 200. That's a pretty big difference. Now watch what happens. So since we have an unbalanced force going that way, it does slow down and stop and change the motion of the cart. So the red team can win. All right, blue team, come on. Let's give the blue team a chance. So again, I'm gonna make it so that the red team starts off winning, okay? So 50 newtons of force towards the red. But wait. Okay, they did it. Yay, blue team. Now if I add this, that's not enough to change it. Blue team wins. All right, so let's talk about what we were just doing, which is called net force. All right, so the first thing on your notes is newtons. So newtons are the units that we're using. So the strength of a force is measured in newtons after the scientist Isaac Newton. So we use a capital N after a number to describe how strong a force is. 3 newtons and 5 newtons, those are very weak forces. You might not even notice this strength of a force. Then if we get up into the thousands, we might be talking like forces of a small car or a bicycle. All right, so we're going to be drawing some free body diagrams. So arrows are used to show the size and direction of forces. The larger the arrow, the stronger the force. The arrow should also be labeled with numbers and units of force, or capital N for newtons. So here are 2 examples of how we can draw free body diagrams. Usually we just use a square to be the object. So this could be anything, could be a shoe, could be a glass of water, but we just use a square. And then we draw forces indicating how strong and what direction those forces are, okay? We draw arrows to indicate the forces. So 3 newtons is not gonna be as long as 4 newtons. Or we could have them going like a tug of war. So these 2 forces are working together. These 2 forces are working against each other, 3 and 5 in opposite directions. All right, let's try it. So if two kids are fighting over a toy, the black box is the toy. One pulls to the left with 10 newtons of force. The other pulls to the right with 7 newtons of force. Draw arrows showing, showing a force of 10 newtons to the left and 7 newtons to the right. So I'm just going to draw on my screen. So it says 10 newtons to the left. So I'm going to draw an arrow and label it with 10 newtons. And then 7 newtons to the right. So it's going to be a slightly shorter arrow. That looks slightly shorter, right? And 7 newtons. So that's a free body diagram. All right, let me erase that. All right, so now we have balanced and unbalanced forces. So balanced forces are the ones that are equal and they cancel each other out. They're equal and opposite in direction. Unbalanced forces are everything else. Unbalanced forces are forces that cause a change in motion. They are unequal. All right, so let's label some of these. I'm gonna do blue for balanced forces. All right, so balanced forces, I'm looking for equal numbers and opposite directions, such as this one. Equal and opposite, like this. Not equal, equal, and opposite. Okay, so those are balanced. To cancel out the equal 0. Now unbalanced, let's change it to red. So 3 and 4, those are not equal. 3 and 5, those are not equal. 30 and 60, and they're in the same direction, not opposites. Those are definitely not equal. So these are unbalanced forces. All right, next slide. Okay, so let me get rid of that. So net force equal is the sum of forces acting on an object. If forces are in the same direction, you add them. So 5 to the right plus 5 to the right gives us 10 newtons. And we give a direction. So this is going to be to the right. Okay, no more writing for me. Okay, 8 and 4, and they're both pointing to the right again, so 8 plus 4 equals 12 newtons to the right. I'm just going to do the 12 newtons. Now, if forces are in the opposite direction, subtract. So these are going in the opposite direction, 3 and 5. So I'm going to take the bigger number minus the smaller number. 3 minus 5 equals 2 newtons. Very good. And which direction? Which direction is stronger? Again, it's the right. So it's going to be 2 newtons to the right. Now this one, it says 18 and 20. They're going in the opposite direction. So I'm going to take 20 minus 18. 2 newtons. Now which one's winning? This one's left. This one's right. The left one is the one that's larger. So this one is actually going to be to the left. All right. Clear that. And what's the next slide? The next slide is you give it a try. So this one is opposite directions. We're subtracting. Big number minus little number. 4 minus 3 is 1 newton. Which one is stronger? The one to the right. So it's 1 newton to the right. What happens if you have 5 newtons and 5 newtons and they're in opposite directions, so we subtract? Well, still follow the same rules. You're still going to subtract. 5 newtons minus 5 newtons is 0 newtons. And there is no direction because they're equal. So 0 newtons. Here's another one. 7 newtons to the right, 7 newtons to the left. Subtract those and you get 0 newtons again. So those are, since they're balanced, they're going to be 0 newtons. This one is also balanced, so it's going to be 0 newtons. You try and figure out this and this. So 5 minus 3, since they're opposites, is 2 newtons. Which direction? Which direction wins? To the right. Now this one's tricky. We have 2 arrows going to the left. So they're on opposite sides of the box, but they're pointing in the same direction. So 30 plus 60 equals 90 newtons, and the direction would be to the left. All right. So that's pretty much it. That's how you find net force. And these examples are in your notes, so why don't you give them a try? We have 60 and 30 going to the right. Add those up. Then we have 10 and 30 in opposite directions. Add them up, and don't forget to put what direction the net force is in, right or left. All right, now let's talk velocity and acceleration. So velocity is speed and direction, okay? North, south, east or west, up or down, left or right. Velocity includes the direction of the speed. Now this is important because acceleration means any change in velocity, which that can mean speeding up because that's a change in speed. It can also mean slowing down because that's a different change in speed, but it can also be changing directions, so turning. That's also acceleration. So this car has a net force of 3 forward, so the car is accelerating forward or speeding up. All right, so is this acceleration? The answer for this one is no, because I am going the same speed for a long time. I'm not changing speed and I'm not changing directions. Is this acceleration? So the answer for this one is yes, because she is speeding up, going faster and faster as she gets closer to the ground. What about this? The answer to this one is also yes, because Jeremiah quickly turns a different direction. That's acceleration. What about this one? The answer for this one is no, because the asteroid traveling through empty space has nothing to speed it up, slow it down, or change directions. All right, that's it for the slideshow. Make sure that you copied in your blanks for velocity and acceleration, and use 2 of those examples that were yes for acceleration at the end of the slideshow to help you with your examples. That's it for this module.